because there's an h bar in the numerator of the ball magneton. So h bar disappears. So anyway, this simplifies to this, right? 1 over r, oh, that's all the same. L dot s, okay, from here. So L dot s. Okay, now let's convert that to, via the correspondence principle, as usual. Let's convert that by assumption. Again, you assume that it's valid, into quantum mechanics. Right now, from an earlier session, that J hat squared is L hat squared plus S hat squared plus 2L dot S. Remember that? Well, we've got an LS here. We've got an LS here. So we can solve for this. Will just be J squared minus L squared minus S squared. Okay. So we can put that into this LS here in terms of J squared L squared S squared. We can put that into this formula here. So our delta E now, well, in terms of your Hamiltonian, let's say. Now, you're familiar with these terms from the Hamiltonian from before, previous chapters, okay? These two. And this is your delta E, in a sense, your extra potential due to the spin-orbit coupling. Right? Now, this J squared minus L squared minus S squared is your LS, and your LS comes from here. So we plug that in, and this F of R, what's that? Well, it's this, right? And why is it 4? Why is it 2? Because of the 2 here. Okay. Because LS would be J squared minus L squared minus S squared divided by 2. So you get a 4 into here. Alright? So this F of R is this. Okay? So here's our modified, if you like, Hamiltonian. That's usual. We've done that before. You've seen that before. But now we have this extra term, right? This extra factor, because we're considering now the spin-orbit interaction. Now, we could keep going. We could keep adding more terms to the Hamiltonian due to other effects. For example, mentioned earlier, for heavy nuclei, the electrons are moving really fast, and then you cannot ignore, because the effect's too large, you cannot ignore the electron-electron interaction, stuff like that. So now in quantum field theory, when we get to it, instead of using the Hamiltonian for technical reasons, there's a reason why quantum field theory tends to use the Lagrangian rather than the Hamiltonian. They're closely related. The Lagrangians can have many terms in them, many factors. And that's one of the reasons why anticipating that the Lagrangians get very long in quantum field theory. I anticipated that. It was one of the reasons that motivated me to buy this very big board, because when I get to grade level courses, physics, I'll probably just write across 2 whole squares. So there won't be any more squares. There'll just be one long rectangle. Okay, so we've got this expression now for the Hamiltonian with this sort of correcting term, extra term, where F of R is the following. Right? Now, even with this, the Hamiltonian like this, you can write out the the Schrödinger time-independent equation, and you can still split it up. You can still separate it into a factor of 2 terms, like a radial term, depending on the R, and another factor depending on the orbital, the polar angles, theta and phi. You can still do that, even with this extra term added. The textbook just sort of threw that in as a mention. All right? Now, if you put a eigenfunction here, here, and here, And so these are operators that now you know that for a given eigenfunction, say whose angular momentum L, big L, has eigenvalue little l, well, big L squared has eigenvalue L into L plus 1. So you call this H hat dashed, right? So that's this part of the Hamiltonian, H hat dashed. So these are operators, and you can look on them as on the left-hand side of an eigenequation. So the right-hand side would have in these positions would have the corresponding eigenvalues, okay, which are this. I mean, you know the eigenvalues for j squared, for appropriate eigenfunctions, of course. J into j plus 1 for this, L plus 1, S plus 1. Okay, so you can rewrite that as this, right? Now, now we get into a bit of a chicken and egg type problem. Which comes first, the chicken or the egg? Here is the textbook writer Davies and Betts making a reference to content in the next chapter, chapter 10, and we're doing chapter 9 at the moment. And chapter 10, its theme is perturbation theory. And I'll talk a little bit just to give you a taste, because what we're actually doing here, this term here is a perturbation, a slight change in the Hamiltonian. Now there's a whole theory about doing that kind of stuff, and this here then becomes a concrete example of perturbation theory. So, and there are formula that will come out of that. I've got the textbook here. Let me just check how many pages chapter 10 is. How much theory is involved. Chapter 9. Oh, it's fairly short. Okay, and nine pages in chapter 10 on perturbation theory. Okay, so here's your perturbed Hamiltonian. In other words, the slight addition, an extra term added to your Hamiltonian. So H hat dashed as this, and from perturbation theory, which we haven't done yet. So this is just thrown at you, right? But you can, once you finish chapter 10, you can come back to this and say, oh, that's why. Blah, blah, blah. Okay, so if this is the perturbed Hamiltonian, like the extra term added to your Hamiltonian here, then perturbation theory says the change in the eigenvalue will be this. Now, this here doesn't change. These are just numbers after all. But what has changed now is you've now got the expectation value of f of r. Okay? So that's the change in the energy eigenvalue due to addition of this extra term, this perturbation, if you like, of h. So you can look on this as your unperturbed Hamiltonian, in a sense the original Hamiltonian, pre-perturbed. And then you add this extra term, so you perturb the Hamiltonian, and so the net result, yes, the unperturbed part plus the perturbing part gives you the total Hamiltonian h bar. Right? So due to that perturbation, you'll get a change in the energy eigenvalues of your Hamiltonian, and that change, delta E, from the theory of perturbation theory, which we haven't done yet, it'll be this, okay? And effectively, the only difference of this and this is this expectation value, right? Now, expectation values depend on, remember, we've said this several times before, expectation values depend on two things. The operator that you're trying to find the expectation value of, and of course the wave function that you're using. You change the wave function, the expectation value will change probably. So in this case, which which wave function are you using? Well, answer is the radial part, the part that depends only on R, of the undisturbed wave function. So that would be the eigenstate of this, right? Before you add this, the radial part of that. And in fact, big R from what we did in earlier sessions. Right? I don't know if you can see it, but so to calculate this expectation value, so you have it, your f of r, it's just this, okay, and the bracket wave function is your big R from earlier theory. So that's big R with the suffix little n l. Right? So you use that R to calculate this. Right? So I'll continue on in the next session.